In this lesson, we discuss the protection mechanisms provided by the page memory systems for protecting and isolating multiple users. We also discuss the virtual memory mapping, which lay out the data and the program area within the virtual memory addressing systems. These concepts lay down the foundation knowledge for understanding buffer overflow attacks, memory leak attacks such as heartbleed, and operating system support for security. Buffer in computer terms is defined as a continuous blocks of memory that can be used for one, data, which can be used to store data for variable, either static, global, dynamic, or local variable, and array. Second, the code. We have user program, we have shared library, we have kernel program that need to work with the contain instruction for execution. To shield the user and kernel programs from each other, the virtual memory is used in modern operating system. Within a virtual memory address space, different operating system and CPU has different way to organize and allocate the buffer for different region of data. On Linux operating systems, the static and global variable are allocated at load time on the data segment. The dynamic and local variable are allocated at runtime on the stack, typically in the higher address space. So they are located at different region. In a modern operating system, every program is compiled and allocated data and code to the same virtual memory address space by the compiler. The code or instructions are generated with addresses located in the lower part of the memory. The data are generated with address located in the upper part of the memory. The concept is shown in the left-hand side of the diagram with 3 users and their data page and code page. And code page are the page contain the instruction. They typically are fixed size memory, 4K for example. Since the system is time shared by all these program and users, and we only have one shared main memory, these common virtual memory addresses to be mapped to physical memory address to avoid these conflicts. No 2 instructions from the same virtual memory address from 2 different users should be mapped into the same physical memory address locations or physical memory page. The instruction from one user should not be allowed to access or steal the content of the data page from the other user. Actually, for the matter, the code page to find out what the instruction is doing. For example, in the right side of these programs, the instruction user N, which is the last user there, their instruction is put in physical memory page 3.1 and should not be allowed, that instruction there should not be allowed to access the data page in page 2.7, which is belong to the user 2 and page number 7. This is achieved and enforced by the page loading mechanism and the booking function of the operating system. And all these addresses will be mapped by Memory Management Unit called MMU, which is a hardware address mapping device to speed up the processing. During the time slot allocated by a particular users, the CPU will only be addressing, retrieving the data instruction of the code page content of a particular users. And so they are not sharing with other users. That when the time slot expires, the operating system will perform content switching, loaded the corresponding physical page and mapping entry in the MMU, so that the particular user will addressing and retrieving the data and the instruction page of the particular user in the main memory, in the physical memory. Here we show the virtual memory map used by the compiler of a Linux system to allocate memory area or addresses to various data and instructions of a user program. Here we use 32-bit memory address as an example. 64-bit, you just consider they are, you have more space in the area. The top 3 table entry show that the top 1/4 of the memory address space is used and reserved by the kernel memory. They are from C3040, C70 to OF kind of address location. The program instructions are allocated with address started from 0804 8000. This is an individual user's program instruction, and upward until you finish all the instructions compiled by the compiler. In assembly language, assembly programming language, we call this region of the program .text segment, and typically in assembly programming code, it will have that particular section label. After that, the initialized program data, like the constant, the strings used in declared in the program, are allocated. We call that region the .data segment. After that, the compiler will put the region of the data with uninitialized program data, such as global variables, allocated in that region called .bss segment. They are on top of the .data segment. After that, the compiler will reserve and point out the area of memory that reserved for heap, HEAP. And this set of this area will be allocated dynamically when a program execute function like malloc, M-A-L-O-O-C. And when that happens, they will allocate a block of address for a particular declaration structure. And we'll start at that address right after the BSSS and go upward and toward the higher address space. The variables created in the heap can be passed along to other part of the program through the pointer. So they are typically longer lasting, and they can persist throughout the execution of the program until they are released. So unlike the local variable in a function, they can persist throughout the program. The local variable, on the other hand, we allocate in stack. On the other hand, they disappear right after the function return. They are released, so you cannot keep them. You somehow need to pass them along through the parameter, the memory allocate to them, so these local variables are released. And therefore, you need to take care of passing it back to the calling function through the parameter mechanism. The shared library code, right now in the middle there, is allocated starting at address 4000000. The stack used by the subroutine call starting address very high, right after C00. Typically, the last address of the first frame is BFFFOF, 7F, and grow downward. They allocate the stack by stack toward the lower address space. And the reason they have heap going up, the stack going down is so that we can have enough space for these two different memory usage. For example, if the stack frame number 1 is the main program and stack frame 0 is for the function foo, FOO, called by the main program, then the frame size, and let's assume that the frame size of stack frame number 1 is 512 bytes. The frame size of the stack frame number 0 is 256 bytes. Then the stack frame could be arranged at the very top from BFFF E0 to BFFF, right? Those 250 bytes at the very top. And then when the function is called, another block of the memory beneath it in that address space, BFFF D0 to BFFF FDF will be allocated. So the stack actually goes downward, okay? But the first byte of those stack frame is actually the lower address of the whole block or address. The more call that being executed in depth, the current frame stack frame will contain the address in a much lower address, and it contains local variable, it contains return program counter, which we are going to discuss in a moment about their structure. Here is another view of the memory layout of a Linux process. The content of the ESP, the extended stack pointer register, which is the current stack pointer register, will point to the lower address of the current stack, lower address, the last byte of the current stack, and which is typically the memory address of the last local variable allocated in that relative functions. The break function call typically will contain the end of the data segment. It is set to the end of the heap data segment that allow the next malloc function request to be allocated with the memory that hasn't been used and toward the high address space. And every time they are called, they are adjusted. Note that 32-bit architecture, ideally, there are 16 gigabytes of memory space. They are to be shared between the user stack and the shared library. And if we look at carefully about the starting address 400 to the address, upper address space BFFF, right? They are to be shared by user stack and shared library. The next block, lower than that, is belong to the runtime heap. They can have about 4 gigabytes of memory space minus the area used by the instruction, the global variable, the constant, the .txt rate segment, the .data segment, and the .bss segment. Depending on how big is in instructions and data, the remaining is used by that remaining 4 byte minus that is used by the heap. Most of the time, space is enough. If not enough, you can move your execution system from 32-bit architecture to 64-bit architecture. But at the same time, you need to have more memory to have that better effects, to utilize those address space. Know that the content of this area are chopped into fixed chunk, fixed size page, they call page, to be loaded into the physical main memory. Some are code page and some are instruction page as shown.